All right. So good morning and welcome to ASIC's seminar series. This is John, the seminar coordinator. Together with me is Ms. Kathy Medley. Kathy is our communication specialist. So Kathy and I will be today's moderator. And just so you know, then the seminar is being recorded and the video will be later available on our ASIC YouTube channel. You are welcome to bring up any questions. You can unmute yourself or chat us. And today we are excited to have our distinguished speaker, Professor Segundo, joining us from University of South Florida. We are also very glad that Dr. Changyong Chao joined us. Dr. Chao is the Chief of Satellite Calibration and Data Assignation Branch at NOAA STAR. So before the speaker gets started, I will turn this over to Dr. Chao to let Dr. Chao introduce the speaker. So Dr. Chao, please proceed.
Okay, good morning. Can you hear me?
Yes.
Okay, great. Good morning, everyone. Welcome to the seminar by Dr. Segundo from University of South Florida. Dr. Segundo received his PhD in computer science in 2013 from the Federal University of Paraná, Brazil. And then he became a professor of the Department of Computer Science at the Federal University of Bahia, Brazil, from 2014 to 2020. And then he joined the University of South Florida in 2020 as a postdoc at the Institute for Artificial Intelligence, or called AIX. And he's currently visiting assistant professor at the Department of Computer Science, Engineering. So I think the chair there is Professor Saka department. So his area of expertise are computer vision and pattern recognition. And one of his interests in remote sensing, which we share a common interest here. And he has worked on land use classification, airplane detection, and COVID-19 impact monitoring, and with projects awarded by IERTA and ESA. And he published several papers on related topics. So I would say it's fascinating to see what AI and machine learning can do these days, such as identify dogs and cats and plants. So certainly we'd like to explore what computer vision can do for us in general, and for the VS satellite images in particular. So certainly we look forward to his seminar. And thank you, and Dr. Segundo, it's yours.
Okay, thank you so much for the introduction, and thank you for having me here. The talk that I'm going to give you today is about monitoring human activity from space with satellite imagery and computer vision. And of course, I haven't worked on this topic by myself. I have worked with many different colleagues, and I would like to thank them for all the work that we have put together. So these are all the researchers that I work with in this topic. And well, you probably know a lot about Earth observation. Most of you maybe have even much more experience in this field than I do. And the combination of Earth observation and computer vision is not a recent research area. We have like many different works, like going back like many years ago. But this research field has gaining some momentum over the last years, and there are different reasons for that. I'm going to talk a little bit about that. And one of the things that usually we think about when we are using satellite images in research is like, what is going to be the cost of that? Like having a satellite on space is something that is very expensive. So can we actually afford to have those images so we can do research? And if we can have some images from space, are these resolutions actually going to show what we need to see to do to accomplish some tests? So are we going to have the resolution that we need to actually accomplish the test that we want to do? And finally, like we are going to be capturing like a vast area through images, and this is going to end up like with a massive amount of data. So can we process this amount of data in time? Like if we take 1 hour to process 1 minute of data, we are never going to actually be able to parse the entire data that is coming from this satellite or multiple satellites. So we have these 3 main concerns, but they are not like fixed concerns, and they have been changing over time. And of course, if we consider the scenario that you have nowadays, things are slightly different, mostly because resolution is increasing every year. And we are not only talking about resolution in terms of like ground sampling distance, we are also thinking about like temporal resolution. So we are revisiting the same location more frequently, and we are seeing these locations with more and more pixels, and this is helping us to see more stuff and probably be able to solve more problems using these satellite images. And besides that, we also like are experiencing like a decrease in the price of these kinds of applications. So satellite images are getting smaller, which means that you can put more satellites in space, and they are going to be also less expensive, and you can have more data, and the price to get this data is going to be smaller. So satellite images are getting more accessible, and we can start working more and more with that. Like one example that I'm showing here, we have now one company that has like more satellites than all the satellites that we had back in 2008, which is not that much, it's not so long ago. And these satellites also have like some resolution that we didn't have in the past. So now we can have like ground sampling distances of like 3 to 5 pixels, sometimes even less than that. So pixels with size of 50 centimeters. And we can revisit the same location every 90 minutes, or depending on the satellite, if you have more resolution, then it's going to take a few days. But in the old times, maybe we take like months to get the same location. And we also have like a bunch of APIs and free data that we can get these days. Not all of these APIs are free, but we can get they have their own APIs, and we can also get structured map data, not only satellite images, and we can combine those things together. So we have a much better scenario these days for research in remote sensing that we didn't have about 10 years ago. And satellite images, they bring like an advantage that not many other technologies can give us. So if we want to do some kind of application that has to have planetary coverage, and we try to use any other technology that is not based on remote sensing, we are going to run into several different problems. Imagine that we want to like capture human activity, but we want to use cell phone data. We are going to have access limitations, so we are not going to be able to access the data from all the cell phones in the planet. We are going to have varying technologies, so we have different carriers that probably have different maybe protocols. We have different technologies in different countries. We do have lack of infrastructure, so maybe some countries are not going to have the information that we are looking for, or some regions in some countries. And we are going to have like language mismatch, so and protocol mismatch. So depending on the countries, we are going to have information coming with different languages, with different protocols. And this is going to be something that is going to be very hard to achieve. So if you want to get global coverage with cell phone data or some kind of technology like that, this is going to be very hard to do. But with satellite data, this becomes very easy. Like we can get information about any part of the globe, and everything is going to be in the same format. And this is a very nice feature if you think about keeping track of human activity anywhere. And when we talk about human activity, there are different also ways of looking into that. Usually people think about the impacts of the human activity on the environment, for instance. But we were looking more into activities related to human development or human interaction. And for this kind of application, we usually require higher resolution images and also a deeper understanding of what is happening in the areas of interest that we have to look into. So I've added in here a few examples. So what could be like examples of development that we are keeping track of? So trading, technology, and concentration. So for trading, for instance, we can try to look into the supply chain through ships or trucks. We can try to measure consumption. We can check the transportation infrastructure. For technology, we can see the capabilities of a country in terms of space technology or energy production or communication. And in terms of concentration, we can see we can try to measure the growth of population. We can try to find overpopulated areas. We can try to predict maybe disease spreading by the concentration of people in certain locations. So these are some applications in this field that we are interested on. And there are two different things that we can look into when we want to check a human activity. And these two types of indicators are land use and moving objects. So land use is basically trying to understand how certain parts of the land are being used by humans, and by getting this information, we can get some understanding about the human activity in those locations. But this is something that is only going to change in a long-term period of time. So if we want to get a faster understanding or get an understanding of human activity in a short period of time, then we have to start looking into objects. So objects are usually movable things that are moved by humans, and if we keep track of this movement somehow, we can also have some ideas of what kind of activities or how much activity, human activity, we have in certain locations. So I'm going to start talking about land use analysis, because this is how we actually started in this field. And then I'm going to talk about how we moved into object analysis to get a better understanding in the specifically for the COVID outbreak crisis. So in land use analysis, there are two different ways we can try to classify the land into one of the classes that you are interested on. So the first one is what we call semantic segmentation. So we are going to try to, for each pixel, to try to say what is happening there. So in here, we have green pixels for the golf court, we have blue pixels for buildings, we have white pixels for parking lots, and we have gray pixels for roads. And this is something that is more expensive, especially if we think about satellite images that usually have a very high resolution, and we might have many different classes for each pixel. So this is going to be something hard to do. Another way is actually trying to find regions of interest using something that is cheaper to compute, and then classifying these regions of interest into a set of classes that we are interested on. And finding region proposals can be done in different ways these days. People use neural networks to come up with ship neural networks to come up with region proposals that are later processed by a more expensive neural network that is going to find the label. But in satellite images that we usually have temporal information, we can think about change. So we can measure the change in certain areas by the difference of the images, and we can find proposals based on that. Let's say that we want to find some new locations that are being built, and we want to know what is actually being built there. We can use the change in satellite images to come up with proposals, and then classify the location to see what this piece of land is being used for. And our first work on that was a solution for this challenge, which was created by IARPA, which was called Functional Map of the Road. And the idea in here was to classify region proposals that were provided by IARPA into one of 62 classes of interest. So they have many different classes. They had airport, they had airport hangar, they had fire station, they could have nuclear power plant, or a waste disposal facility, or a wind farm. So they had many different types of locations, and we would get some proposals, and these proposals could be one of these 62 classes, or it could also be none of those classes. So we had to actually be able to discard proposals that were not interesting. That's the whole idea of the challenge. And to come up with a solution for that, we also had to comply to some restrictions. So we had limit time for training and limit time for inference. So our solution was not actually just the results for the classification results for the images that they gave us. We actually had to provide them a complete solution that they would run in their computer, respecting the restrictions that they created. And the computer was also limited, so we couldn't have like any computer that we wanted. We had to use one of these two machines that they specified. And by having this time restriction, they are actually simulating a realistic scenario. Like we have limited time to process a certain batch of data, like we have in real life. Like we have a limited time to process all the data that is coming from the satellite image. But we had to be creative because we had this restricted time, but we also wanted to get a good performance in the challenge. So and we knew that at the time, the best way of getting good results in classification was through ensemble of classifiers. So basically the idea of ensemble classifiers is instead of training only one classifier to solve your problem, you train several classifiers and you try to combine them to get a better result. But you cannot train all of them in the same way, otherwise they are going to like have a very high agreement in between them and they are not going to complement each other. So we had to find like ways of diversify the output of these classifiers, and you can do that through different techniques, different initialization to your models, different approaches, different training data. And like the whole idea of Hydra is trying, which is the method that we developed for creating ensembles of classifiers for land classification, is to actually create diversification in a fast time. So create diversity, sorry. So we want to force diversity, but we also want to run fast. So the whole idea is instead of having several classifiers and trying to diversify our training since the beginning, we first actually try to solve the problem a little bit, and we reach a point where we have a decent solution for the problem, and then we try to force several copies of this classifier to get some diversity. So we try to force our classifier, several copies of this classifier in here that we reaching here, to get like different solutions in a pool of optimal solutions. So imagine that training a classifier is an optimization problem, and you don't have only one good solution, you have a pool of good solutions. We want to reach different points in this pool of solutions, because each of these points probably runs slightly better for a few of the classes that we have interest. And if we have classifiers in different locations in this pool of solutions, they are going to be complementary to each other, and they are going to get a better combined result later on. We are using neural networks for that. So at the time we participated in this challenge, the most popular neural networks were ResNets and DenseNets. So we use these networks. And again, since our training time was limited, instead of training these networks from a random initialization, we started the training from a popular database that has nothing to do with satellite images. ImageNet is a database for classification of objects like dogs, people, fish, and things like that. But it learns like basic features from colored images that are useful for other problems. So we start our training from this point, and then we train it for some time using satellite images, and we stop the training. As I said before, we train for some time, and we stop when we have like a decent solution, but not the perfect solution. And then we create several copies of each of these classifiers. So we have in here diversity in terms of methods, because we have two different networks, and we will have also diversity in terms of like data, because we are going to use slightly different variations of the data in each of these copies of the networks to learn a slight modification of the problem that can probably give us like some complementary information in the end. So we use like different areas around the area of interest. So instead of cropping like a tight bounding box around the region that we are classifying, we extended this bounding box to get some context around this region. We also use multispectral data in here, but instead of actually using all the 8 bands that those images had, we used the version that was actually a PCA over the bands that was compressing 8 bands into a 3-channel image. So even though it looks like the regular RGB image, this is like a combination of all the 8 spectral bands. We also tried different augmentation operations. So we would apply flips on the images, like to mirror the image horizontally or vertically. We also applied some zoom operations to zoom in or zoom out from the images. And we try like different class A weightings. So basically we are trying to modify the training data for each of these copies in here to get better results. And then we can just fuse the results of all these models to get a better result. And fusion is very simple. Basically each model in here is going to vote for one class, and we can just do a majority voting in here to decide on the label. With this result in here, we managed to get like a very good result in the competition. But not only that, like we managed to train an ensemble in half of the time. So we actually simulated one ensemble that would take 14 days to train, and our ensemble only required 7 days to train. And we actually saw that we were able to get the same result as this ensemble that was more expensive by dividing our training in 2 stages. First training only one model, and then splitting it into several copies of the same model, but training on different data. So this idea works very well for satellite data, and we can reduce the training time. At the time, the training time was the major restriction for us. So we didn't come up with any solution to speed up the inference time. But of course, for satellite images, this is going to be important as well in the future. And one thing that we observed is that the common mistakes that our method is doing, they are very similar to mistakes that humans will do. So it's classifying here shipyard as ports or hospital as educational institutions. And when you look like from above, from the sky, it's very hard to know if something is a port or a shipyard, if it's a hospital or an education institution. So these kind of mistakes are not bad mistakes, I would say. It is still classifying things that look similar to each other. So the confusion is very specific in this case. It's not like a generalized confusion. They are not confusing shipyards with hospitals, for instance. Our method is not confusing that. And then we also think about how to improve our method to not only speed up the training time, but also speed up the inference time. And one idea that we had was to, instead of splitting the training, we could actually split the neural network. So I don't know if you know how neural networks work these days, but basically they have like several layers of like very basic operations that are combined together over time until they have like very specialized features, like characteristics that not characteristics, sorry. They learn some features, like some very specific features for each class. So the first layers are very generic, then they start to getting more and more specialized into certain patterns, and then in the final ones, they are like the ones that are capable of doing the classification. And we could actually split our neural network in a way that we can learn basic features that work for all the variations of the problem that we are going to feed in the input. And then when we start like dividing or having training data of different types, we can actually like split our network and learn features for those specific types separately, and can keep doing that. And this kind of strategy is not only going to speed up training, but also inference, because instead of using n different networks as we are using in here, we are going to be using one network that has some forks, and the cost in here is going to be comparable to like log n. If the cost of the inferencing one network is CI, the cost of inferencing this network is going to be something like CI log n instead of MCI for using n models with cost CI. So this would be a nice way of like increasing the speed. another thing that we worked on was using language semantics to filter out bad labels. So instead of simply like getting the output of the neural network for each region that we want to classify, we would get like the best solutions, like the top 3 or the top 5 classes for each bounding box. And then we try to find this set of labels for these bounding boxes that would make more sense together. And we use like the concept net, which is a graph that has like the semantic relationship between concepts. And we use the labels for these bounding boxes, like shopping mall, parking lot, road, garage. We use these labels as our concepts. And we knew that like from the concept net graph, it's more, it's common that we are going to have like a road close to a parking lot and a parking lot close to a shopping mall, but you are definitely not going to have like a nuclear power plant close to our hospital, for instance. So these kind of things maybe we can learn from concept net, but we even like think about like how to improve this even further using structured map data. So imagine that we can get annotations from Openstreetmap or Google Maps, and we can learn like which locations appear close to which other locations, and we can learn relations between these locations in here, and we can like discard labels that don't make sense together. So that's the whole idea in here. So we are not only working with images anymore, but we start learning with semantics, and we can improve the results in remote sensing by using semantic relationships between locations. But land use can only give us like so much. Like as I said, like we can only see like long-term activity because land use doesn't change so frequently. So if you want to look into short-term human activity, we have to actually look into objects, and for that we do need higher resolution images. We can see buildings like in images with lower resolutions, but sometimes we cannot see cars in those images. So we start working in here because we did have an in-house vehicle detector, and we wanted to use that for some nice application. And when the COVID-19 crisis started, we realized that we could use like the detection of certain objects to actually see how the human activity was affected by all the lockdowns that were imposed, or some activities being like shut down. And we wanted to do that, like to try to collaborate with authorities as well. So we wanted to be able to create some measures for social distancing, for instance, and possibly identify areas that we could experience a rise in the number of COVID cases and inform these numbers to authorities. So that was the idea of this pipelining here, where we would use structured data to find regions of interest, and then we would detect objects in these regions and try to come up with some numbers. But we had some problems with the number of data. So we didn't have temporal sequences with enough images that we could do like some analysis, some automatic analysis. We were not able to find the standard behavior before the outbreak, and even like measure the behavior after the outbreak to come up with some automatic way of deciding if there is something different going on. But we could like see some changes. Like in here, you have like the number of ships that are parked in a North Korean port, and we had like a lot of ships over there and this was not common before. Same thing here, we have a construction facility, and we can this is a hospital construction actually, and we can kind of see that from space because we can detect trucks, we can detect excavators, and we can see that some construction is going on there. And during COVID, we might guess that this construction is being used for hospital if it started during the pandemic crisis. And in here, we could keep track of like vaccination facilities, for instance, or testing facilities by counting cars on lines. But I think these ones are more interesting. So we could actually measure the impact on tourism, for instance, because we could see that the number of cars in the parking lots of rental facilities increased after the COVID outbreak. Same thing for the number of airplanes. Like we didn't have so many flights going on, so we had more airplanes parked on the airports, or we had less cars on toll booths because people were not traveling so much. So this kind of measure would be more interesting, but we didn't have enough temporal resolution to actually come up with something automatic in here. And we actually did something when we found this contest, which was a contest organized by the European Space Agency. They were looking for ideas on how to use satellite data to monitor and mitigate the COVID-19 situation. And these ideas could be in any of these three applications. And you can see here that human activity was one of them. And the advantage of participating in this contest is that we received access to all the data from the Earth observation missions from the European Space Agency. And this is what we are looking for. So we had access to Sentinel-2 images, actually the entire history of Sentinel-2 images that was collected since, I think, 2015. And Sentinel-2 images have a ground sampling distance of 10 meters. So we cannot see cars. We can barely see some big objects like airplanes. But we decided to give it a try. We wanted to originally detect parked airplanes in the airports because we expected this number to increase. But while we were inspecting those images, we observed a very interesting phenomenon. Like we first saw that like in the lanes of the airport. Like we saw that when airplanes were departing, we had this like interesting colored motion blur effect. So the airplanes appear like in three different colors because we are looking into RGB images, of course. But if you have multiple spectral images, this effect actually happens in all the bands of the satellite. And well, this actually means that we could see moving airplanes, which also implicates that we can detect flying airplanes, which is something interesting. We could actually measure the traffic of airplanes around an airport, which is something that is even more useful than the number of parked airplanes, because sometimes some airports are not being used like for airplane parking. Only a few airports are being used for airplane parking, and we would not get like a very good idea of what was happening in different locations of Europe in this specific contest. So we wanted to exploit this motion effect in here. We saw some images before the COVID, and we could find like these airplanes easily. By the way, the reason for this motion blur effect is color parallax. So the multispectral instrument from Sentinel-2 images has a small temporal offset in between all the bands, and this causes actually the object to be capturing slight different positions for each band, and also the satellite is in slight different positions in each of the bands. So we do have like this color shift caused by the satellite movement and also because of the airplane movement, and we can observe the two reasons together. So you can see here the direction of the satellite is going like from the top to the bottom of the image, while the airplane in here, you can see by the tracks of the airplane, you can see that it's moving from the left to the right. So you can see that we have the two effects actually acting together to create this colored pattern. And sometimes we don't have tracks. One reason for that is that like both satellite and airplane are going in the same direction, or just because the airplane is not as big or doesn't have like a cloud track as other airplanes. So there are different reasons for not having a track. This is actually not as frequent. Most of the airplanes that we detect, they don't have these tracks, but these tracks are very useful for us to understand the two parts of this motion blur effect. And another thing that we observed is that if we try to look for airplanes after the COVID, it's very hard to find. Like in this image, I actually went through all the imaging here, and this image is very big, and I couldn't find any airplane. So, well, this is a good thing. Like maybe I could try to train a detector that will do this automatically, and I can measure the impact of the COVID into air traffic. So we just adapted our previous framework. So you can see that this image is similar to the image that I had before. So instead of having like different regions of interest that could be supermarkets or hospitals, in this case in here, our regions of interest are always airports. And then we get images around these airports, and we use a neural network to detect these airplanes, and then we can run some analysis over the number of detected airplanes to try to come up an indicator that can help people somehow. So just going fast, we use 30 different airports, and we don't use information for all the airports for training, because we want to be able to see if the detection works for other airports, because if we want to extend this idea later on for other airports, we are not going to have access to all the images that we use for training, especially because we need to annotate airplanes, and this is something that takes a lot of time. And to actually find the location of these airplanes, we got data from Openstreetmap. So if you search for the IATA code for each airport, you can get the boundary of this airport, and then you can actually get the center of the bounding box that for this boundary as the location for this airport. This is what we did. Then we used the Sentinel Hub, that is a platform from the European Data Cube for actually storing all the images from Sentinel-2 and other EO Earth observation missions as well. And we use this platform to download the images. So we download a very large area around the airport, because we don't want just to see airplanes really close to the airport. We want to have like a good window of observation, and this area corresponds to like a 20-minute window of observation, which means that we can detect arrivals that are going to arriving up to 20 minutes in the airport that we are looking for, and also departures, all the airplanes that departed up to 20 minutes ago from the airplane, from the airport. So this is what we can see in this kind of image. These are long, big images, and if we have like enough data annotated, so if we have the locations for the airplanes in this image, we can train a neural network that can detect airplanes. We come up with this architecture in here because we wanted a very small architecture. We didn't want to use the existing architectures because they are usually big and they are trying to solve very complicated detection problems. I would say that our detection problem is a little bit easier because we always have these 3 colored dots, and our problem is that we have vast amounts of data, so we want something that is really fast. So our network actually looks into 51 by 51 pixels patches into this image, and for each of these 51 by 51 pixel regions, we say if this region is centered into an airplane or not. So this is our detector basically, and with this region we can detect airplanes flying up to 1800 kilometers per hour, which is twice as much as the typical commercial speed, so flight cruise speed. So basically we can detect airplanes with this neural network, but we do need like annotated data, and this is something that is very hard to do, right? We have like huge images, and airplanes are such a small thing in those images that is very hard for a human to go through like several images. Imagine going through all the images from 15 airports. It will take forever. So what we did was actually something semi-automatic. So we just annotated a few images. So we took 18 images and we coarsely annotated it. So we looked for like the most visible airplanes. So we annotated 190 airplanes in these 18 images from only one airport. We train a first detector only with those images. And then we run our detector in our training data set. So in the images that we wanted to use for training, and we just inspected the detections. So for every detection, we cropped a small image patch around this detection. And then we manually decided if this detection was actually an airplane or not. And this was much easier to do. Like instead of looking through like huge images, we just had like a few thousand patches, and we had to classify these patches as airplane or not. That's all. And in the end, we were able to find about 1,800 airplanes in all our training images. We did not use all the images from all those airports. We only got a range of, I think, 3 months from all the airports for training. And in the end, we got a detector that was very reliable. These numbers here are not maybe straightforward, but what they mean here is that for the training airports that we had, 15 training airports, we had 7.6 false alarms per month. And in the testing airports, we had 10.1 false alarms per month, which means that we only detect one, we only have like one detection that is not actually a plane per month. Not one, sorry. We have less than one detection per month in each airport that is not actually an airplane. All the other detections are airplanes. So this is very reliable, and we could use this kind of information to come up with some other analysis. In here, you can see many different airplanes that we can detect using our method. These ones are the ones that are easy to see. These ones we magnified because they are very hard to see. You can see that our approach works even like for very small airplanes that we can barely see the RGB dots in the image. It also works under occlusion, so sometimes the airplanes are in the edge of the image and we don't have the 3 dots, but we can still see them. Or if you have occlusion because of clouds, you can still see them. And during takeoff, we don't have the color parallax effect due to like high altitude, but we still have like due to speed, and we can still detect the airplanes during takeoff as well. So we can detect airplanes in many different situations. Oops, sorry. And the false detections are usually caused by noise or cloud parts. We have like some images, they are stitched together, and we have like some artifacts in these regions. So this can cause false detections as well. And we can also have some, in some cases, some false detections caused by like some colored dots in the land, or even like some large trucks in the roads that create the RGB pattern as well. And we wanted to know if we were detecting the airplanes like in the correct location. So we got some flight records and we plotted the airplane tracks at the time of the acquisition of the satellite images. And you can see here the purple circle, the pink circles are the estimated location of the airplane at the acquisition time of the satellite image, and the yellow circles are the detected airplanes that we detected. And you can see that we are detecting airplanes where we have image and we have pink circles. Sometimes we don't detect it. Sometimes like the airplane is too small. There can be like different reasons. Sometimes we don't have an image in that region and we cannot detect these airplanes. But we can definitely use this information to check the impact of COVID on air traffic. So you can see here the air traffic around one airport before COVID and after COVID. And you can see here, this is in Germany, and you have a lot of airplanes in the air before COVID, and after COVID, the number of flights is much lower. Even though we don't detect like some airplanes that are small, you can see by the trajectory in here that this is a small airplane, same thing in here. So sometimes we cannot detect like very small airplanes, but we can detect most of the airplanes, including airplanes during the takeoff that sometimes they don't have the track for these airplanes yet. The major challenges were, of course, clouds and noise in the ocean parts. So sometimes sun glint generate all these colored dots, and airplanes are colored dots. So we have many false detections in those regions. We also saw the clouds also cause a lot of false detections. So we had to kind of address those issues. And the way we did that was by, instead of running our analysis in the entire image at once, we divided our images into small blocks, and we ran statistics only in blocks that have good information. So we discard blocks that have too much cloud data, or that don't have image data, or that have so many detections because of the noise. Like we know that airplanes are not close to each other on sky. So if we have too many airplanes in the same block, this is probably caused by noise and not by real airplanes. So we can discard these blocks as well. So after discarding the blocks that are not good for our analysis, we can combine the average number of airplanes in each of these blocks together, and we can come up with an observation for the entire region. And if we get all the images that we have in a month, for instance, we can have a month observation for this airport. And if we do that over time, we are going to have the history of observations for this airport, and we can also analyze the behavior of the human activity in this airport, the behavior of the air traffic in this airport. So in here you can see one example. This is the airport of Dublin and in Ireland, and you have the expected number of airplanes in a month, that is 5.6, and during the COVID you can see that this number go much below this reference number, and these red areas actually align well with the periods that we have high restrictions in flights. So we could see through this information that we could actually measure the impact of COVID through our monthly observations for different airports. And by running some analysis into that, we try to come up with some recovery measurements for each airport. And I'm showing here three different examples. We have 2 airports in regions that are very touristic, like Palma de Mallorca in Spain and Athens in Greece. And we also have Manchester in here, which is the only airport that we observed a decrease in the number of flights after the initial recovery after the first COVID outbreak. And we were able to observe some correlation between the recovery rate in the airports and the number of new COVID cases. So especially for these 3 examples that I said, these airports that have a big recovery in the number of flights also had a big number of new COVID cases, while this airport in here was the only one with a decrease in the number of flights also experienced a positive correlation with the number of new cases, which means that the number of new cases was also decreasing. So this, of course, doesn't mean that the number of flights implicates into more new cases of COVID, but this is something that we can use to identify areas that require some attention, and we can give this information to the authorities. But I think that one of the nice results that we got in here is when we try to come up with a measurement for the impact of COVID in Europe, in the air traffic of Europe. So we just computed the average observation for Europe, which was the average of the observation for the 30 airports that we had. And we compared that to the real number of flights. So the solid line in here is the impact of COVID measured by the real number of flights. And this number comes from 42 countries and includes all the airports in these 42 countries, all the flights, anytime. And in our case, we only have sporadic images, the revisit time for Sentinel-2 is about 4 days, and we have incomplete data because we have clouds. We also have noise in the detector, so we have some detections that are not correct. But even with all those problems, when we combine all the airports together, we come up with a measurement of the impact of COVID that is very similar to the real one. So the dashed line in here is the measurement of the air traffic in Europe using our data, and you can see here that it is very close to the real data. And this actually shows that we can not only use that for air traffic analysis, but if we do use the same framework for other things that we can detect, we can guarantee that we have a similar detection performance, our framework would work as well. So if we can detect cars in hotels, for instance, we can quantify tourism. If we can detect ships in ports or trucks in highways, like I show in the example that some trucks can be detected also by the same effect that we detect airplanes. We can try to evaluate the supply chain using the same idea. And even for flights that we do have the real information like in here. So you might think like, why should I like detect flights in satellite images if we can get it like in a cheaper way from these flight records online? You can find like some applications where you can combine both information. One idea in here is to subtract the detected flights from the flight records and try to see if you have like untracked roads somewhere. So I don't know if you know, but in Brazil we have some huge problems with some drug traffic over the Amazon. We have like a bunch of flights over the Amazon carrying drugs. And these flights, of course, they are untracked. So if you can detect airplanes and maybe run these over time, we might be able to figure out like some roads that are being used by drug dealers that will not show up in the flight records. But we still have like to have the flight record data so we can know which airplanes are not an issue. And well, as a result, we did receive an award for this solution. So it was one of the best contributions of the race contest, and it was fully integrated to the race dashboard. So if you if you Google race dashboard and access it, you are going to see the air traffic indicator, which was created by us and integrated to the dashboard. And a description of everything that we developed is available in this publication in here. And we made our code and data publicly available, not only for this work, but for all our previous works as well. So if you want to use some artificial intelligence for remote sensing and you think that what we are doing might be useful, everything is available. And you can also feel free to contact us if you think that we can help you somehow, or if you want to collaborate in any project. And yeah, that's all I have for today. So I'm open for questions if you have any.
Thank you, Dr. Segundo. If anyone has any questions, you can go ahead and unmute yourself and ask it. Or if you don't have a microphone, you can just send me the question in the chat. Oh, I have a chat question. Can you explain more on how the moving airplanes exhibit tracks and different colors in the satellite imagery?
Okay, sure. So let me go back to that. This slide in here. So, okay, so imagine that we are capturing the different bands with our satellites, right? We actually have on Sentinel 2, I think, I don't remember the exact number, but I think it's 11 or 13 bands. But we are only using 3 that are the band for the red color, another band for the green color, and a third band for the blue color. But the time that we acquire these bands is not the same. So imagine that we had like one object flying in the sky, and we are it's not moving like a balloon, not an airplane. You need to remember, you need to know that like our images, our bands, they are aligned based on the ground level. So the way the satellite images like don't have like a motion blur for any objects is because we align all the bands together at ground level. Which means that if we observe an object at a different altitude at different times, it is going to appear in different locations in the ground level. So if we observe the red band at this position in the satellite image, we are going to see the airplane in here, in this location in our image. Let's say that this is our image plane. And then the satellite is going to move a little bit before it captures the green band, and then it captures the green band. And even though the ground is still in the same location because we are registering the images in the ground level, the airplane is going to look like is going to appear in a different location. And again, when we capture the next band, the airplane is going to appear in another different location. So this is the first reason why we have like these 3 different colors in here. But we also have movement in the airplane. So let's imagine the opposite scenario, the satellite is fixed, but it's capturing the 3 bands at different times, but the object is moving. So again, the ground plane is fixed, but since our object is moving, the red band is going to capture the airplane position in a different location, in this location in here, and then until the satellite captures the next band, the airplane is going to be in a different location. So the airplane is going to appear in a different location in the green band, and finally it is going to appear in a different location in the blue band. So this is going to create an image that everything at ground level is going to be aligned. So you're not going to have any motion blur, but everything that is above ground level or that is traveling at a very high speed at any altitude is going to have like this RGB effect, because they were the object was acquired in different locations. You can think like that. I don't know if this responds to your question, but I just tried to spend some more time in this explanation.
Thank you. I'm sure they'll say so if they have additional questions. We do have a chat question from Daila Zhang. She asks, will various pixel sizes affect the results, i.e. larger pixels on the edges of the field of view versus smaller pixels in the center of the field of view?
You mean this like by the original images in the satellite images, right? We are not using the raw images from the satellite images. All the images that we use, they were already corrected, so all the pixels have the same size. So we actually don't even have access to the raw data from the Sentinel-2 images. The only data that we had access through the Sentinel Hub, which was the platform that we could download the images, were these rectified images where all the pixels had the exact same size, which was 10 by 10. So all pixels had covered a region of 10 by 10 meters. I don't know if this was the question, but like in the raw data, you do have problems with pixels with covering different areas, but in the rectified images, you don't have this problem.
Daila, you're free to unmute yourself if you want to engage in a dialogue there. Or not, that's totally fine. I have another question from Ron Vogel. He says, so the parallax is not unique to the Sentinel-2 instrument, but the technique will be applicable with other satellites too.
Yes, any satellite that has like a time offsetting between the bands can see this kind of pattern as well. Yeah, and again, as I told you, this is because we are only using the RGB bands, but this actually happens in all the multispectral bands. So if we like had a way of like visualizing 8 bands together, and all the 8 bands, all the bands from Sentinel from the Sentinel-2 satellite have a time offsetting between them. So we would actually see like more levels of like displacement in between the points in all the different bands. So we would have like, instead of 3 points in here, if we use 8 bands, we would have like 8 points in sequence showing like different locations for the airplane in all these 8 different bands.
Okay, thank you.
Oh yeah, I was just going to say that this is like us taking advantage of like a certain characteristics of this satellite to detect this kind of movement. But like if other satellites have other kinds of information, we can always try to look into what kind of information those satellites are providing and trying to take advantage of those types of information to come up with solutions. So this is just how we came up with the solution for this problem. And in this case, Sentinel-2 is very good because it has like this effect. But for other problems, maybe this effect might not be so useful. It can even like make the problem worse. I don't know. Sometimes having motion blur is going to make our life harder. Like imagine if you had motion blur at ground level, this would like it would make us like it would make harder to detect buildings, for instance, because the building would not appear in the same location in each of the bands. So depending on the problem, this is something that is useful or not. Oops.
Do we have any other questions?
Can I have a question?
Yeah.
So if we can use satellite data to generate or create some new data we don't have from other network, like example, we can create a data for the whale global, the activity of the whale in the ocean, right? So or some birds migration from summer to winter, winter to summer. So I mean, through the machine learning, we can create a lot of stuff. So we don't have, and those data can be used for either for climate, for oceanary, or the ocean fishery. So so your air traffic is very cool actually. So, but we have a very good data set for the air traffic, right? So FAA have all of this data. You can use this data set of training your machine learning, making more accuracy. Yeah, just cross-checking from different data set. Yeah, so we're in the AI age, right? A lot of things can be done. So that's a good talk. Thank you.
Oh, thank you. Yeah, and yeah, I agree with you. Like, basically, like as long as we do have like the data, and we can either come up with annotations or or we do have annotations for the data somehow, we can design a new neural network, or we can use neural networks that already exist to solve the problems and try to create models that can do predictions or classification or regression, depending on the problem, of course. So yeah, it can be used for other applications as well. As I said, as long as we do have data and we do have annotations, and we can even try to come up with ways of using like unsupervised techniques. So even when we don't have annotations about the problem, if the problem is something that is like very evident in the data, we can try to use some unsupervised techniques to come up with clusters of pieces of data that make sense together, and maybe identifying some phenomenon based on these clustering results.
Yeah, so there's other thing that I saw you have image for the suburb, I mean the big area cities, suburb rating based on their house shape, the distance between those houses. You can figure out that those communities most house built in 1950 or 1970 or 2000. Then you can just, I mean, this information for construction companies are very interesting for this. They help them for their planning. Construction stuffs. So
yes. We can use artificial intelligence for that. Yeah.
Are there any other questions? Last call.
I got a question. So do you think it's possible then you use the same method to detect and calculate the cloud motion?
You mean to use one method like that to detect clouds and
right?
Yes, actually, I think even Sentinel, we are using Sentinel Hub to collect the images, and they already have a classifier that for each pixel, it says if the, I think here, yeah, when we collect these images in here, we are not running a cloud classification because Sentinel Hub already provides a cloud classification that is for each pixel in the image, it gives us a probability of the pixel being a cloud. And this is something that we can train, right? Like imagine that we have a set of images and we have someone to manually annotate the areas where we have some clouds. We can then later try to use all the bands from the satellite image to try to predict if a certain pixel is a cloud area or not, is covered by cloud or not. So if the pattern for clouds is something that a human can observe in the images, then we can definitely have a neural network that can do the same kind of classification.
Cool, thanks.
And then, of course, if we have like a big revisit time, like in some cases, like imagine that we have a revisit time like the one from the space company. In here, like they have a revisit time of 90 minutes. So if we have one image every 90 minutes, we can even try to track these clouds. So if we segment the cloud every 90 minutes, we can try to later on like align these clouds and predict like the movement of those clouds in the near future.
Thank you. Any other questions before we conclude?
This Cheng, I just want to thank you for the excellent talk. I personally learned a lot, and now I know there is a RAPI, and so they are doing the intelligence work. I guess it's what functional map, and so classify buildings based on the function, and also there is the airplane monitoring. So those are very interesting. And also the Sentinel-2, we haven't used much, but probably we can. And actually currently we're using the Landsat for geolocation. And so I know Landsat 9 was recently launched, but we will compare the Landsat with the Sentinel-2 and see what we can do to enhance our capabilities to monitor the geolocation of the satellite images. So there are now opens up a lot of opportunities. What we can do is moderate resolution images, which is what we have. And I think that this will be an exciting area for AI and machine learning. Again, thank you, and also thanks, Dr. Professor Saka and team from USF and the AI Institute.
Sure.
Thanks.
Thank you for having me here again. Thank you for the invitation, and thank you all of you that show up for the seminar today.
Absolutely. Thank you, everyone. I think that concludes our talk today, but everyone can join us next week as our seminar series continues.
Thanks.
Have a great day, everyone.
Bye-bye.
Okay.
Bye-bye.
Bye.